Welcome everybody. So today we're in the, I'm trying to remember how these things are called now, workshops, 2-hour talks about polynomial and moment optimization in Julia and JuMP. So this is a joint presentation by Tillmann, Benoît, Chris, and myself. Lea unfortunately couldn't make it. So I guess let me tell you, I'm going to very briefly just give you an overview of what is polynomial optimization, how does it fit within JuMP. So it's definitely very integrated to JuMP, which is the optimization or mathematical programming library in Julia. I will kind of call it maybe somewhat of a sub-community, and I'll explain why. So for instance, the Gitter channel for JuMP actually has 2 channels. One is JuMP Dev, which is mostly development around JuMP, and Sum of Squares. So, and there's a reason why there's 2 channels. There's slight difference, and mainly it's because everything that has to do with sum of squares or polynomial optimization is also very strongly linked to other packages related to algebra and polynomials in the Julia ecosystem. So in some sense, it's a little bit of a combination. And some of the packages that are related to sum of squares are sum of squares, PolyJuMP, which takes care of polynomial optimization in JuMP that Benoît will explain in detail, moment optimization that Tillmann will talk about, and Hypatia, which is a solver that is a pure Julia solver, interior point solver that actually can work with, use and solve this problem much more efficiently. And this is fairly big community. It started growing with a whole bunch of people. It keeps growing. And as I said, it's still very closely connected to JuMP. So for instance, the JuMP 3, JuMP Google Summer of Code projects, they all basically were focused on JuMP, but all of them in one way or another were actually strongly connected to polynomial optimization. So I'm going to mention the 3 GSOC students, Arpit Bahitia, Guillermo Bodin, and Gilles Pfeiffer. And so without further ado, I'll give you Benoît, who will start with the actual content of the talks.
Okay, so this is an overview of the 3 parts. So I start talking, and then Chris and Tillmann will do the other section. So I'll explain briefly the new version of JuMP and why in the new version of JuMP, there is everything you need to create an extension of JuMP to other domains. So here we will explain how we extended JuMP to polynomial optimization, but basically most of the work was done in JuMP to make it easily extendable. So you can really reuse most of the work to extend it to other more domain-specific extension of optimization. So I talk about JuMP. I talk about the bridges mechanism, which is used by sum of square and the sum of square extension of JuMP. Okay, and then Tillmann talks about the moment of extension of JuMP, which made use of sum of squares, and Chris will talk about the Hypatia solver. And basically, the thing is that sum of square creates sum of square constraints. And this sum of square constraint can be reformulated into semi-definite programming. So if you use any semi-definite programming solver, you want to reformulate this into semi-definite programming constraint. But if you use Hypatia, which supports sum of square constraint, you don't want to do this reformulation. And so this will be achieved by bridges, which are automatically enabled if needed. And so the sum of square bridge, if you use an SDP solver, you will see that it doesn't support sum of square constraint, it will bridge it. And if it sees Hypatia, which Hypatia will just tell, I do support sum of square constraint, you don't need to bridge it, and it won't be bridged. But you see that it's a much more general framework, and it works for basically any reformulation used by JuMP. So I start by what are these bridges, and what's MATLAB interface, the new interface of the new version of JuMP. And then so that will show you how to actually extend the interface, so it actually extend add new modeling facilities and actually be able to expose new structure also to the solvers. Not only, so this will illustrate this with sum of square, but you can imagine doing this for many other situations. And then we see that we can also extend JuMP. So in addition to allowing more to be able to expose more things to the solver, you also be able to extend JuMP, which allows the user to even have a very nice interface to give this new structure. And then we talk about how we use all this mechanism in sum of square, and if we have time, we'll talk about reshaping things, because in MATLAB interface, we have to vectorize kind of everything. And somehow when you show it to the user, you want this vectorization to be transparent, so you want to reshape things back in the original form. Okay, so first the bridges. So I started by briefly introducing what's the MATOMT interface. So that's the low-level interface that we use for the solver. So we have basically three mechanisms. So one mechanism which had a variable, so either add variable, we add a free variable with no constraint, or add constraint variable, which can add a constraint variable or constraint variables. For example, you can say I had a non-negative variables, or you can say I add a matrix, which is a PSD variable. And then you can add constraint. For instance, you could add, say, I want 2x plus 3y to be equal to 1 when x and y are variables. So once you have created variables, you can add constraint on them. And the constraints are formulated in the function in set. So you have some function of the variable which is either basically quadratic or affine or nonlinear, and then you have the set which is the set in which this function should belong. So basically you want to tell the solver you need to find values for this variable such that when you evaluate the function at the value of this variable, it belongs to this mathematical set. And then we have the set get functionality, which basically allows you to set and get any kind of attributes to the model. So this is kind of extensible, but like the most use case is objective function, which is an attribute. So you give an objective function to the model to guide actually the optimization, to give it a sense of what's the optimal solution, what is the, among all feasible solutions, which one do you want? The one that maximizes or minimizes this objective function. So the advantage of this new framework, and that's kind of why we written the interface, is that it's very generic. So for this constraint, for the constraint variable or attributes, we have many things defined in MOI, but you can basically extend it very easily. So just by defining new kind of function, new kind of set, new kind of attributes, you can totally extend the capability of MOI. And all the infrastructure of MOI is kind of try to be generic on the function, set, and attributes that it uses, and so nothing in MOI almost is specific to the attributes, function, and set defined in MOI, and everything can work with custom things you can create. And so we'll use that in sum of squares to create custom variable and constraint, which are sum of square variables, sum of square and constraint, and also new attributes that we'll need for our domain-specific extension of JuMP. So to introduce bridges, I will first explain all bridges I used independently of sum of squares. And the best example, I think, is with sum of square programming. So a sum of square solver, usually it only supports a very small amount of things, but still you could solve a very large class of program with that. So SDP program, usually it only supports non-negative variables, SDP variables, and equality constraints, and that's it, nothing else. But still, you may be able to write a JuMP problem like that. So if you see here, none of the variables are non-negative, none of them are PSD, and the constraint, none of them are just equality constraints. So to give this kind of problem to a PSD solver, you need to reformulate kind of everything. And so this is a huge work, but what we did with MOI is we kind of broke it into very, very small spaces. So each piece is called a bridge, and a bridge is kind of a recipe of a reformulation of some constraint or variable into an equivalent form. And just by combining all these little pieces, you can reformulate this huge model into a model that is supported by the PSD solver. So the advantage of implementing this in terms of bridges, instead of adding like in each of these PSD solver, you could say, instead of just saying they support equality constraint, non-negative variable, and PSD variable, you could say they support like every kind of things, and then you have to do all the reformulation in the solver. The problem with this is that it's a lot of work for each like single solver, and the number of solvers is growing, so that's kind of unscalable. And then also, it's not very nice because the solver kind of claims that it supports some kind of structure. It is not true. It is just reformulated internally. And so when you're trying to know how should I formulate the problem for a specific solver, you have no way to know like what's the native way things are presented to solver, and you don't really have a way to evaluate is that going to be solved efficiently or not. So you basically want the solver to only say what kind of constraint does it natively support, meaning by that which kind of structure does it actually explode when solving, and the rest it can just say it's not supporting, and it will be just be bridged automatically. And then when you write the model, when the user writes the model, he usually want to represent the most structure about the problem as possible. So usually you can solve a problem more efficiently if you know more about your problem, if you know specificity of the problem. And you want the user would like to represent the structure even if many solvers probably don't support that. Okay, so the best way to do that, and that's actually the example of Hypatia, which can actually exploit the structure of the sum of square constraint. And so the user would like to represent the structure for Hypatia to use, but then if you use another PSD constraint, it doesn't understand it. So you would like still say to the user, you can use this advanced representation, and don't worry about all the solver, it will be transformed automatically by bridges. So that's kind of the philosophy. Here's a few examples of bridge. I took the simplest one. So a simple example is the flip-sum bridge. So basically, if the user say, I want to create a variable larger than a lower bound, and the solver only supports creating variable lower, smaller than a lower bound, you can just, instead of creating the variable x, you create a different variable y in the solver, and then the variable created by the user would simply be minus y. And so every time the user uses x, you need to replace it by minus y for the solver. And if the user creates a constraint smaller, like linear function smaller than some constant, you can just transform it by multiplying by minus 1. Okay, so another example of bridge is if you create a variable which is larger than some constant, instead to the solver you can create a non-negative variable y, and then the variable of the user would be y plus the lower bound. And so for instance, PSD solver only supports creating non-negative variables, but now with this variable vector bridge, it can also create it variable larger than some lower bound. Okay, so these are all very simple simple bridge, but combining them we can actually make something more complex. So for example, the free bridge allows to create three variables, which was not allowed for PSD solver. The slack bridge, this one is very important. So if you look at the SDP solver again, you can, all the constraint you can do is just equality constraint, and then you can create either non-negative variables or PSD variables. With the slack bridge, basically, if you have a constraint which is some, like a fine function of the variable should be in some set, what you do with SDP solver is instead you create variables in the set, and then you add equality constraint between the function and the variables. And for an objective function, if you want to minimize some function, and let's say the function is quadratic, this is not supported by PSD solvers, what you do is you create a slack variable x, you minimize x instead, and you say f is more than x. And then you get closer to what PSD solver supports. Okay, so this is an example of, for example, if you add an interval constraint to a PSD solver, what are all the bridges available and what you're going to do. So here you see that on the top you have the interval constraint, and on the bottom left and bottom right you have constraint actually supported by the PSD solver. So the PSD solver on the bottom left, you see it can support creating non-negative variables. On the bottom right, you see it supports creating equalities, and all the arrows are bridges that are available. And so in JuMP, you have the list of all the bridges, and you have the constraint the user wants to create, and you have this graph of all the possible transformation you should do, and you need to figure out how you should transform this interval constraint into things supported by the solver. And in some way, you should try to generate the minimum amount of constraint variable possible so that the final problem is easy to solve. So one possibility is you start from the interval constraint, you split it in two constraints, and then you vectorize both of them. And then for the one that belongs to non-negative, you flip the sign to create a function that belongs to non-positive. Now you have two constraints belonging to non-positive, and then you create a slack so that you create non-negative variables. This is supported, and then you have an equality between the slack you have and the function, And this is a vector affine function in 0, and then you can create one constraint by entry, and you have a list of just linear inequalities. Okay, so that's just an example to illustrate what's the idea of bridges. Each bridge is like an atomic transformation, and you just want to mix them to do a large transformation of the whole constraint. And so the problem we faced is, how do you actually decide which bridge to use? Right? So looking at the graph just before, you have a list of nodes. So we say that each constraint or each variable in some set is a node. And you have a list of hyper-edge. So for each bridge, the bridge starts from one node and then ends up at multiple nodes. So if you look at the split bridge, over here it starts at this node, and there is two outgoing nodes. Okay, so the outgoing nodes, it's all the constraint or variable that the bridge creates, and the starting node is the constraint or variable that is being transformed. Okay, so this is a summary of this. So there is also objective bridge, but I skipped that for simplicity here. So now if you think about it, the selection of a bridge is kind of reminding us of multiple dispatch in Julia, when you also have kind of the same thing. You have a function and you'd like to apply it to a list of types, which is the type of the entries, and you'd like to know which method should I use, right? So it's kind of similar, but it's not the same thing, because here there is several bridges. Like you could have several methods for a single signature of a method, and usually what Julia does is it takes the method that is the most specific, thinking that the method that is the most specific is probably the most efficient because you use more structure. But here, for bridges, is not the same, because there is some bridge that's probably transforming your constraint to a constraint which is further from the constraint supported by the solver than the one where you're starting from. So you need to somehow have some sense of, okay, you are playing this bridge, are you getting closer to a model that is supported by the solver? So you cannot just take the bridge that is the most specific to the constraint you have. And a second thing is so in Julia, if you define a method like plus AB equals something, then you basically define an infinite amount of method, because AB could have any type, right? So if you do not specify concrete type for your method, you're basically defining an infinite amount of method. And we have the same thing here. So Julia, that's the reason it's just in time, because it cannot know ahead of time which method it needs to compile. And it cannot compile it all because there is an infinite amount of method it could compile. And here it's kind of the same thing. You basically have maybe an infinite possible number of functions and set, and you don't want to build a full graph and compute the shortest path for all the nodes in the graph. So what you do is kind of the same thing. Just-in-time bridge selection. Every time the user creates a constraint or want to add a variable or an objective, you will see. So in Julia, what it does is it sees which new method it needs to compile, and here we see which new nodes we need to consider, and from which new node we need to find like what's the optimal bridge. So basically, in a few words about the algorithm, you have a set of bridge which we suppose fix. And we have a list, so we have a distance function which says for a node, it's either not defined if the node has not been considered yet, or we have some distance, which is kind of, so this is used as the heuristic for which bridge we select. The heuristic we use is we're trying to find the minimal number of bridges to bridge the constraint that is added into constraint variables that are supported. So the distance from a variable is the minimal number of bridges that should be used to bridge this variable. The distance from a constraint is the same, the minimal number of bridges that should be used to bridge this constraint into supported constraint variables, and the same DO is for the objective. And so we either have the distance which is already defined because the user have already tried to add this constraint or variable, or it's not defined yet, which means, so it's the same as in Julia, if a method is already, the compilation of a method is either already done, you can just call it, or you still need to recompile, and then you first compiling, and when you add the method again with the same type, no, it's already compiled. Here is the same thing. Either the distance is already defined for this type, and you can just use the bridge, or you need to figure out which bridge you use. So first, you need to find all the nodes for which you need to compute the distance. So for example, in this example, if you start for the interval bridge, and suppose you have not considered any node yet, all the nodes here, you see that you need to compute the optimal distance from there. So you basically do a DFS. You start from the node where you are, and you explore all the nodes you can with the bridges. And for all these nodes, you will need to figure out, should I go to this node or not? So you need to compute the distance for all these nodes. Okay, so you do a DFS starting from the type you have, and you have a list of nodes for which you need to compute the distance function, and then the last step is you use some kind of Bell-Malford algorithm to compute the minimal distance from this node. Okay, so that's the bridge mechanism in MOI. So how do we use that for sum of square? First, I briefly explain how you can extend JuMP. So basically, you also want to have the user to be able to use the add constraint macro in JuMP and still use your new type of constraint you have defined in MOI. So it's kind of simple. You don't have to create new macros. When the user writes a macro like that, what happens is that JuMP called this build constraint method. So the error function is just, you can use it to give a nice error, which also shows to the user the string of the constraint he has called. And then you have the function and the sets. So when the user says that a function of the optimization variable should belong to a set, it basically calls this function. And if you have a custom set or a custom function, you can actually catch this function with multiple dispatch and do something custom. So normally, in most of the case, what it simply does is, if you have a vector of JuMP function, it should belong to an MOI set, it simply creates this vector constraint. And then you call add constraint with this constraint. And what it does is simply it takes this function in terms of MOI variable, it takes this set and it passes to MOI. So basically to the solver. And then it creates a constraint reference with the index and so on. And so what you would like to do is create either a custom type of constraint here or a custom type of set, and then you probably want to do something different here. So it's very generic what you can do. It's really first JuMP call build constraint with what it had in the macro, and then you can return something, and then it will give that to add constraint, and then you can do something custom. So depending on your extension of JuMP, you either want to implement a custom build constraint or a custom add constraint. So in our case, we only define build constraint, but you see that for moment op, we also define add constraint. So for instance, we have the second order cone in MOI where you need to give the dimension of the cone, but we also have a second order cone set in JuMP where you don't need to give the dimension. So we just define this build constraint here, and what we do is that given this second order cone, we create the MOI second order cone looking at the length of the function to define to get the dimension. And that allows to give to the user further convenience that he doesn't have to specify the second order cone dimension. A more tricky example is for the PSD cone, where the user you want to give a symmetric matrix of variables and or a find function of the variable and say this is PSD. And so in MOI, there is only two kinds of constraints, either a scalar function in some scalar set or a vector function in some vector set. There is no matrix of function. So we need to vectorize this. So what we simply do is we implement this build constraint. We check that it's square, of course, and then we take a vectorization of the upper triangular part of the matrix. We say it should belong to this set, which is it's triangle because it's a triangular upper part, so it's the PSD set basically, and we return this constraint. And we don't have to define a new add constraint because we just return a vector constraint. And I think if with your custom constraint, you also want to add a new bridge, because usually JuMP only knows about the bridge defined in MOI, you can return a bridgeable constraint. So we'll see that with JuMP. So the bridgeable constraint, it contains another constraint. So it could be several nested bridgeable constraints, and the bridge type that needs to be added. And when JuMP sees that, it first add the bridge and then add the constraint. So how do we use that in sum of square? First, I need to briefly mention what's sum of squares. So the idea is quite simple. When you have a quadratic polynomials, if you want to know if it's non-negative everywhere, you build this matrix Q. And so there is a unique way to find this Q, such that P of X is X transpose QX. And then you just check if Q is positive semi-definite. And in fact, if it's positive semi-definite, you can compute the Cholesky decomposition of the matrix. And you can see here that from the Cholesky decomposition, you can actually get a sum of square decomposition of the polynomial. And so once you have that, you really have just a certificate independent of just the solving you've done. You can just tell to someone, oh, just on the top of my head, I found this decomposition of the polynomials, and no, I just proved you that it's non-negative. But in fact, for non-negative polynomials, it's equivalent. It's non-negative if and only if you can find this decomposition. But if you don't have a quadratic polynomials, but instead of polynomials of degree 4, for instance, you can do the same trick. The only difference is there. In the X vector, you can not only put variables, but also monomials. But here again, if the Q matrix you find, no, it's not unique, but if you find some Q matrix which is positive semi-definite, again, you will be able to find a certificate that your polynomial is non-negative. So you see that this is a sufficient condition. If you find this Q matrix positive semi-definite, you know that the polynomial is non-negative, but this is not if and only if. So Hilbert's proved that there is only 3 cases where it's if and only if. So for univariate quadratic and bivariate quadratic polynomials, you have that there exists this positive semi-definite Q matrix if and only if the polynomial is non-negative everywhere, but that's not the case. For other situations, there are counterexamples. But they didn't find any counterexample, and we had to wait since 1967 to have the first one. And the Motzkin polynomials, in fact, it's non-negative everywhere, as you can see in the plot, but there is no sum of square decomposition of the polynomial that can show that. Okay, so how do we define this? So we'd like to define this sum of square decomposition. So basically, we want to know if some polynomial is sum of squares, but instead, we create this Q matrix, and we ask a PSD solver, just check that this Q matrix is PSD. Okay? So you just tell the PSD solver, just look for some PSD matrix Q, such that X transpose QX is equal to P. So you create a PSD matrix, you create a linear equation in your variables, and then if the solver finds this Q, then it means it's sum of squares. If it doesn't find this Q, it's not sum of squares. And then if you use Hypatia, you just give these polynomials, and it will solve it differentially. Chris will explain. So you'd like to define a bridge which explains how to transform sum of square constraint into PSD constraint. And so the basic idea behind bridge is that if you can have 2 sets such that linear image of the first set is equal to the second set, then you have basically everything you need. You see how you can transform the constraint, transform variable in the set, and also see how you can transform the dual back. So if the user asks for the dual of the sum of square constraint, and you can ask for the solver what's the dual of the BSD constraint, and you can transform it back to the dual of the sum of square constraints, and so on. So in the sum of square code, you see that you're trying to find some matrix Q such that X transpose X equals X transpose QX equals the polynomial, and this is simply if you look at the mapping between Q and the polynomial X transpose QX, the mapping between the elements of Q and the coefficient of the polynomial is just a linear mapping. So you have a linear mapping between the PSD cone and the sum of square cone. And so because of this, you can create a bridge with this mapping, and you will have the dual and so on working. just by looking at the matrix A, the transpose, and so on. And in fact, you can just define a variable bridge. So you see, if the user says, I want to create sum of square polynomial variable, instead you create a PSD variable, and then you say the coefficient of the polynomial that the user has are in fact equal to A times the entries of the matrix. And if the user creates a sum of square constraints, it can just combine first the slack bridge to say the coefficient of this constraint are equal to some slack, and the slack is a sum of square polynomial variable, and so to create a sum of square polynomial variable, you can use the SOS polynomial bridge. So in fact, only by creating one bridge, we can support sum of square variable and also sum of square constraint. And when the user would like the dual of the constraint and so on, we can use the formula we have here. But we can also create actually new attributes. As I told you at the beginning, attributes is very flexible. If you create new attributes, for example, the user would like to get this Q matrix or the dual of this Q matrix and so on. If you want to give access to this to the user, it's actually hidden inside your bridge, but the user on the underside is just using JuMP. You can just create this new attribute, and when the user asks for this attribute, because these are constraint attributes and the constraint are bridge, MOI will understand that it has to ask this question to the bridge. So you will, in the bridge, you will get the call that the user would like this attribute, and you will be able to return the value of the Q matrix and so on. And to extend JuMP, what you simply do, if the user says some polynomial is in the SOS code, you just implement a new build constraint, you get the coefficient of the polynomial and the monomials, and you create an MOI set to represent this sum of square cone with these monomials. The coefficient of the polynomials would be the vectorized version of your function. It depends on it's a vector of, let's say, a fine expression of the decision variables. And then so this polyjump that bridgeable is just going to figure out which bridges it needs to add, because in fact, in practice in sum of square, we had a lot of bridge, but you could just use bridgeable with the sum of square bridge here. And so it has this vector constraint, which is the sum of square constraint, and then it has this bridgeable which says to JuMP, you should also ask the sum of square bridge in case you don't have it. So that when the user uses the sum of square constraint, automatically you will add the bridge because it's probably needed, and you will add the constraint. Okay, so I have 5 minutes left, so I'll briefly go through reshaping. 2 minutes? Okay, so it's next speaker. Okay, just a small precision. This is a special session which is 2 hours, so it's until 5:45. It's not like the other session which are only 30 minutes. So yeah, Tillmann, you can come. So quickly reshaping, I told you that we vectorize the polynomials to give it to MOI, and basically when the user wants the dual or to show the model, he would like to not to see the vectorization because it didn't use that, but instead the polynomial and so on. So you need to explain to JuMP. So we gave a special shape here, polynomial shape, and you need to explain to JuMP that when he has to MOI things, it will be vectorized, and you need to transform it back. So basically, we have this system for the PSD constraint. So when you create a PSD constraint, it will be vectorized by just taking the upper triangular part of the matrix. And what the user asks for dual and value and even like just seeing what is the constraint, like what is the matrix of function in the constraint, you need to reshape things. So what you simply do, so you need to explain how to reshape sets. So you also transform the PSD cone set into positive semi-definite cone triangles. So you need to explain how to reshape, and then also need to explain how to reshape a vector of the upper triangular part into the full matrix. And so for the polynomial shape, we had to create this MY set, and if we want to get back the sets used by the user, is the PSD code, which is stored in here. So that's what we do. To reshape the vector of the upper triangular part into the matrix, that's what we do. So we create a matrix, we fit it, and then we return a symmetric matrix. And in the polynomial case, if you have here the vector of coefficient of the polynomial, you can get the polynomial back using this function. So you give the coefficient in the monomials. And for the dual of a polynomial constraint is usually interpreted as a vector of moments. And so what you say is that you create this measure, taking here the value of the moments and here the monomials. And here you need to explain also to JuMP that when he asked for the dual of a constraint, what he will get is not a polynomial shape, but in the dual shape, which is a moment shape. So you simply have to say that the dual of a polynomial shape is a moment shape and so on, so that automatically JuMP, when he gets asked for the dual, he knows that the shape of what he gets is not in the shape of the constraint itself, or maybe in the dual shape. And so you need to define this. And that's it.
Question maybe while Tillmann is walking over to the podium.
Okay. Hi, everybody. I'm going to talk about another JuMP extension, which is actually built on top of sums of squares. So if you have the image still in mind, you had moment opt, then sums of squares, then into JuMP, and then to a solver. And this is joint work with Benoît. And I guess most of you don't know what a generalized moment problem is. So my talk will be first about what is a generalized moment problem and why it is interesting. Then how you can model this with moment, how it is modeled in moment opt. Then what is the relation to positive polynomials, and in the end, how can you solve problems, generalized moment problems. So generalized moment problem is basically an LP. So I hope that everybody in this room knows LP. So what you have is you have a vector x, which is entry-wise non-negative, and you want that some matrix A times x equals B, and you want to minimize the scalar product between C and X. And the generalized moment problem is basically the same, too fast, except that now your variable is actually a measure, and you take the scalar product of your measure with some polynomial, and here you have a polynomial vector, so you take also this scalar product, and your matrix, your measure is constrained to be a measure. M plus means measure, and this K means that is supported in some set which is given. And in particular, we need that all our data is given in polynomials. So, but if this is too abstract for now, just think of a linear problem and replace the variable by a measure. So what can you do with this? The standard example is polynomial optimization. So polynomial optimization, you're given a polynomial, you want to minimize it over a set X. And the problem you probably know about is if you use a local method and you start in the wrong point, you end up in a local minimum, but you want a global minimum. So this you can reformulate as a generalized moment problem by replacing your variable x by a measure. So instead of evaluating f of x in some point x in k, you integrate with respect to some measure supported on k. So easiest thing is you just integrate with respect to the Lebesgue measure, the dx you all know. This might not give the optimal value. What you can do is you can add some density, so you give more weight here in the middle and less weight on the boundaries. This might help. Or the optimal thing to do is to integrate with respect to a Dirac measure. So a Dirac measure which gives all its mass to one single point. And this is actually what we are doing here. So integrating with respect to a Dirac measure is evaluating in the point x. So you see that that the generalized moment problem is a relaxation of the original problem. And actually, it's not even a relaxation, but it's equivalent. So the optimal value here is bigger than the optimal value here because it's a relaxation. And then if you look over here and to replace your f by the optimal value, so by this line here, and you integrate this line, you see that the optimal value is actually bigger than this. By linearity, you can take out the pop. So this optimal value here. And this is the only constraint I have here. It's that the mass of my measure is 1. So I can forget about this and have this. So here you see the optimal value of the polynomial optimization problem is equal to the value of the generalized moment problem. Okay. Now, so this is one application of the generalized moment problem. And now you might not care about optimizing global optimization. So how about volume computation? So say you're given a set K and you know it is contained in some box B. You might be interested in knowing what is the volume of my set. So I have a little skits like that. So here is your box, and you want to find. So here the idea is you want to find to know the volume of the biggest ball in this box here. And a generalized moment way to write this is to optimize over two measures. So the nu is actually a slack measure. So what I actually want to write here is that the density of my measure mu is not bigger than the density of the Lebesgue measure, the uniform measure on the box. So this is encoded in this constraint here. And my measure mu should be contained, so should be supported only in my set K, which here is the ball of radius 1, and nu is supported everywhere. So it's a slack variable. It takes the rest of the mass. So and basically what's happening is we're blowing up a balloon inside. The mass the density inside the balloon is the same as outside the balloon, without knowing any physics, but the shape of my balloon is constrained by being inside the set K. So the optimal measure will actually be the uniform measure on the whole box restricted to my set K. So this will be the optimum here, and this giving me exactly the volume of the set K. Okay. So now global optimization and volume computation might not be interesting to you too. So next example, partial differential equations. So here, you don't see everything here. I see it. Okay. but it's not much missing here. So basically, we can consider scalar hyperbolic conservation laws, which is just you're searching an L infinity function y that satisfies this differential equation here. We are given some initial condition and maybe some boundary conditions. And here I'm restricting to a very easy setup, so everything is scalar, and f is a polynomial. Yeah, I assume unique solvability here. I could add more constraints to make the solution unique, but then I don't have enough space on the slide, so I just assume that the solution is unique. And the problem here is always that this function here depends non-linearly on y. And yeah, here on the right side, you see a generalized moment problem formulation of the same problem. I don't want to dig too deep into it, but basically what's happening is we define a measure on the space, the time and space, and the range of my function y, and a measure in the end. And basically what we do is we multiply this by test functions. So our test functions are ti xj, and we do integration by parts so that the derivatives go over to the test functions. And then here you see basically your differential equation again. And you add some other constraints, and you end up with one huge generalized moment problem. And again, the point here is that this expression now is linear in mu, and this is linear in mu t, and here it was nonlinear in the unknown y. This was maybe too abstract, so I have an easier example. So if you know a Burger's equation, this is dty plus dx 1/2 y square equals 0. You have a little scaling factor in here. And what you typically want to do is you want to consider Riemann problems. So you're looking at a function which is 1 for x less than 0 and 0 for x greater than 0. And you want to see how this evolves. And if you run the code, example burgers.gl in moment_opt.gl, you will get this graph, which is actually a solution of this differential equation. Okay. I don't see the lines here, which is okay. So this was kind of the motivation. I hope you are motivated, and you know that you have seen that you can do a lot of different things with only one tool. And next, I want to show you how you can actually implement this. So how it is implemented in moment opt and how you can use moment opt to solve generalized moment problems. So first thing what I did is I created a JuMP model. So this is an abstract JuMP model, so it's a subtype of abstract model. And I only show the first part here, and the second part is going to be later. And here I just gather the data. So what I want to have is I want to have an objective function, that's here. I want to have constraints, they're here. Maybe I want to have names for my constraints to refer to them. And I want to have measures. And because I defined it as an abstract JuMP model, I can actually use the JuMP syntax and the JuMP macros as Benoît explained before. So when I want to create my JuMP model, I would just do JMP equals JuMP model, a GMP model, as you would do in JuMP. And then I would add an objective by saying add objective GMP in the sense of the optimization and the scalar product between my function and my measure mu. And same for constraints, I would add, for example, this. So what is a little bit different for now is that I don't have an add variable, but I have an add measure, which looks like that. So I would add a measure to my model with the name mu and say that this measure is acting on the variables x and y, for example. So implementation of this is fairly easy because JuMP is generated this way. So just to use this add objective macro, I only need to define this function, the set objective function from JuMP. So it would take a model, an objective sense, and some abstract moment expression, and it would return. What it would do, it would set the value of a JuMP objective to a moment objective with the sense and the moment expression here. So this is fairly easy. For the constraints, you have to work a little bit more. Because usually you would probably enter your constraint like this. So you would say that my moment here is less or equal than 1. But what's happening in JuMP when it parses the macro, it would create an affine moment expression. So it would rather do something like that. So it would bring the 1 to the other side. So you need to, what I defined is this JuMP build moment constraint. So the macro calls this function here. It takes and this build constraints takes an error message, then the function, which is this affine moment expression here, and a set, which is in this case here less or equal than 0. And I just tell it to return a moment constraint with this affine expression and the set. Now, I don't want to have an affine moment expression. I want to have a moment expression on one side and the constant on the other side. So I want to have a form like this actually. So this moment con of affine expression would actually call this function here, and it would set the it would return a moment constraint with the moment expression on one side and being in the set where the constant is shifted into the set. Right? So the output, if I enter one of these those two, the constraints which is added would actually be dot mu f and then MOI less than 1. Okay, so this is the constraint that would be generated. Now we have to add it to the JuMP model. It's happening here. So you define the JuMP add constraint to a JMP model. It can also take a name. So if you specify a name here, it would return the name. It would return the name here. And basically, what I'm just doing is I push the moment constraint and the end of the constraints of JMP, and I push the name and the end of the constraint names, and then the macro, the function returns a constraint ref to this constraint, and it says that it has the moment con shape, and this moment con shape is only an abstract type, a subtype of an abstract shape. Okay. So here is a short example for the volume. So say you want to compute the volume of the set K, so which is the circle, and it is contained in the unit box. Yeah, you would have to define this monomial vector, which can I go back? Yeah. So here we have these constraints here. So I want to generate these constraints. As I'm doing here, but I generate monomials, and I have to interpret them as polynomials. And what I'm doing here is I define a function which gives me the right-hand side of my constraint, so the moments of the Lebesgue measure. So this is basically this. All this you can do without moment opt. And then you would call this in moment opt. So you would create a new JMP model. You would add a measure mu acting on x and y and being supported on k. You would add a measure nu on x and y supported on b. you would add the objective that you maximize the mass of mu. And then you would, with this line, you generate all the constraints that I was showing before. Okay, so much about modelization. Yeah, I haven't told you how I model measures yet, and this is maybe the most urgent question for you, because a measure is an infinite dimensional object, and this doesn't fit in a computer, right? So for this, I have to talk about the relation between measures and positive polynomials. And this relation is actually duality. So if you think about your generalized moment problem just as an LP, it has a dual formulation. So the dual of this will actually look like this. So you would add a dual variable for this constraint here, P. Then the objective becomes maximizing P times B. And the constraint will be C minus P times AX, being in the dual cone of the measures. And the dual cone of the measures is actually the non-negative functions. So here the dual reads like we want to maximize some expression under the constraint that a polynomial, so this left-hand side is a polynomial, is non-negative on K. So now after having heard the talk of Benoît, it's not surprising what I'm going to do. I'm going to replace this greater or equal than 0 on K by belonging to some certificate set, which is a subset of polynomials. And what you can think of here is just being a sum of square, right? So being a sum of square guarantees that this polynomial here is non-negative everywhere, and there are slightly more complicated certificates which tell you that it is non-negative on the set K. So this is what's going to be happen. And this is why when I'm going to define my measure mu, I will tell it what certificate it should use here in the dual. So this is how my measure looks like. My measure has a name. It has some variables. It has a support, which is a semi-algebraic set. And it has this certificate here. And by default, I just set the support to be the full space and the certificate to be sums of squares. Okay, and because this measure is now not a JuMP variable, I had to create this macro here. Yeah, on my own, but this is, yeah, it's a bit ugly, but you just have to create this block here, block quote, where I say, okay, I create a measure with the name acting on variables and having some optional arguments, and then I add the measure to my generalized moment problem. So, and yeah. So Benoît is trying to convince me that I should use variable instead of measures, because then I could have containers as a normal JuMP variable. He might succeed in doing so. So for the moment, I cannot use containers here. Yeah, I cannot define like a whole bunch of measures. I have to define every measure on itself. Okay. So now we really have the whole modelization, and now the question is, how do we solve moment problems? And this is, again, going by duality. So here, on the upper left, I have my generalized moment problem as I modeled it in moment.opt. So this is what I model. This has the dual here, which I already talked about. And it has a strengthening by replacing the non-negativity constraint by belonging to some certificate set. certificates, replace it by sums of squares if you want. And this is an STP or a second or a sums of square problem if you solve it type hash here, and as such has a dual. The dual I don't describe because it involves a lot of additional notation. But basically what I'm going to solve is this relaxation of the problem I model. I model a problem and I solve a relaxation. So this is the problem that will be solved in the end. Yeah, and so before I go on, I want to talk about the second half of my JuMP model. So inside my JuMP model, I have its dual, which is a JuMP model, and I have some bookkeeping which tells me how I find my measure in this dual model and how I find my constraints in the dual. And you have to say, overall this modeling process, I don't create the JuMP model. So I create a JuMP model actually only when I call relax JuMP order optimizer. JuMP means, take your JuMP model. Order means to which order, in which sense ever, you want to relax your problem, and optimizer is with which optimizer you want to solve the problem. And this function is actually here. I hope this works. Yeah. How do I zoom? Yeah. How do I zoom? It's kind of slow. It's okay. Is it readable? And so this is the relax function, and this is doing all the work to solve or to relax the problem. As I said, it takes the JuMP model, the order to which I want to relax it, and the optimizer. And first of all, which it would do is it creates an SOS model in this dual space, in this dual container here. Then here, it will create the dual variables, so this vector p I mentioned in the dualization. So it creates variables in the dual for each constraint, and depending on the objective sense, yeah. So this is if I have an equality constraint, this variable will be free. If I have an inequality constraint, this might be a non-negative or a non-positive variable. So this is coded here. And then here, I'm actually creating this polynomial. This polynomial here. So I'm building this polynomial based on my data. So for every measure, I have a separate polynomial, and I always add the function of the constraint, so the moment expression, and multiply it by the variable, which is the dual variable here. So this is how I generate this dref, and the cref is actually for each measure. I will have one constraint, and this will be the polynomial I created should be part of this certificate set. I give it the domain, so the set K, the support, and here the relaxation order tells me something more about how I want to use this certificate. So here, if it's sums of squares, for example, this will say that it's sums of squares of degree up to 2 times order. Okay, so this is the constraints added to the dual model. Then I still need an objective. This is, the variables times the constant, so the right-hand side of my moment constraints. And then I will just optimize my dual and get the solution of the dual. And as they are actually there's no duality gap here, so the solution of this will be the solution of this. Here. Yeah, so this is what I just said. So where is my solution? To define the objective value function for my JuMP model, I just look up the objective function of the dual, the objective value of the dual. And for my measures, what do I get for my measures? It's a bit more complicated. So mathematically speaking, if your set K is compact, then your measure is uniquely determined by the sequence of moments. So if you know all moments for like really all moments, then you know how to integrate with respect to your measure. On a compact set. And when I solve a relaxation, I can get the moments up to order 2D. And this is actually what I will retrieve from the relaxation. And the way I look it up is I just use the sums of square functions Benoît had defined. So he has defined this variable moments, which is the dual of the equality constraints. When you get the equality, the polynomial inequality polynomials equal sums of square, for example, then this will be the moments. Okay. Future work is quite a lot to do. I mean, I started 6 months ago, so the most important thing for me is to get different moment bases. So for now I just use the monomials as the basis for my monomials. And related to this is it is kind of numerical unstable. So you can get a lot of numerical problems when you look at these equality constraints. So we want to try other moment bases, and this will actually be implemented in this package. Then I want to look at different certificates. So for now, we only have talked about one certificate, this sums of squares, but there is a whole branch of mathematics talking about different certificates. Their names: Krivine, Polya, Schmidtgen, Bisos, Sonk. It's a lot of different certificates, and I want to use all of those. So I want to be able to access all of these different certificates. So we're going to work on this, and also about using sparsity and symmetry in these certificates. So this is a big thing to do. Then more on the modeling side, we want to support moment matrix constraints. So for now, my constraints are just linear expressions of the moments, and here I want to have matrix constraints. So for example, moment matrix being non-negative. I want to implement moment substitution. So if I say the mass of my measure is 1, I don't want to create this variable. I just want to replace it from the beginning. So I mean, mass of a measure equals 1. This corresponds to a variable in the dual, right? And I don't want to create this variable. And a last point is I want to go even more high level and allow constraints that only constrain the measures, and then automatically translate them to constraints that involve moments. So, for example, a measure mu equals a measure lambda if and only if for all moments they are equal. So I would like to implement a high-level language of this. So that's all from me on my side.
Any questions while Chris sits up?
If you could just go back to your last slide. Do you have an example for your first, for the multivariate bases? So do you have an example of a type of problem that you would then be able to solve with that you couldn't do now, or set up a problem? Or is it merely just the properties?
It is the properties. So what you get is when you're working around zero, then the monomial basis is quite a bad idea to deal with, because it's you get a high. So when you work with high degree polynomials, you would have some coefficients which are really big and some coefficients which are really small, and this produces ill conditioning. So there it would be easier to use the Chebyshev basis, for example, to equate the coefficients. So Chebyshev is one example we want to use. But in general, we want to support user-defined bases. Okay.
One last question. Can I ask from here?
Sure.
Yeah.
Okay. So do you have limitations to the kind of measure constraints that you will be able to model? Or
I mean, they're not modeled yet, so.
Yeah. Given how you're going to do the bridge.
I mean, if you can express it as a linear constraint on the moments, then you can implement it. Did you say that?
This is getting filmed? Okay, so I can't swear. I stand by the mic. I can't carry the mic. All right.
Oh, okay, we did it.
The video is focused there. It's being broadcast live.
I'm going to swear. Oh, no internet.
Oh, it's back.
Back? All right.
So you can do view, present.
Yeah. I might just make available offline in case the... Oh, can't do that. Well. All right, so fingers crossed here. All right. Okay. Hi, everyone. This is joint work with Lea Kapelevich, who's another student at the Operations Research Center at MIT, and our advisor, Juan Pablo. So, Hypatia.jl. What does the name mean? So, Hypatia was a Hellenistic Neoplatonic philosopher born around 355 AD in Alexandria, and she taught astronomy and philosophy and mathematics. And she was interested in, cones, and actually her story is portrayed in this movie in 2009 by Rachel Weisz. It's really good. So she was interested in cones, and particularly conic sections. So that's why we named our conic solver Hypatia. Okay,
briefly, agenda. So first I'm going to introduce conic duality and conic optimization. Then I'm going to discuss Hypatia solver, very high level of the algorithm. There's not a ton of math here. Then I'm going to talk about what we call natural versus extended formulations, and run some tests to show that actually, doing things with more natural formulations can really have a big advantage. Then I'm going to look at some applications of polynomial optimization and briefly talk about complex polynomial optimization, which is a generalization of everything we've been talking about. And I won't have time for number 6, which is a code walkthrough. Like I said, this doesn't really include much code. It's just high level. So when Hypatia source code is actually released, which should be in the next few weeks, you'll be able to look through that yourself and maybe use this presentation as a bit of a guide. Okay, so conic optimization. Ooh, that's not great. So a cone is a set that is closed under non-negative scalings. Now, K is called a proper cone if it is closed, convex, pointed meaning it doesn't contain a line, and solid, meaning it has a sort of strict interior to it. Some standard proper cones that you've probably heard of are just the positive orthant. That's sort of the LP cone. Second order cones, positive semi-definite cones, which you can just take the lower triangle and vectorize, and maybe exponential cones or power cones. These are sort of standard because they're the only ones that other conic solvers currently recognize. Now, the dual cone of a proper cone is also a proper cone, and we call it K star. And it's the set of all vectors that have non-negative inner product with all vectors in the cone K. All right. Primitive proper cones are cones that cannot be written as a Cartesian product of lower dimensional cones. So if K is not primitive, then we can decompose it like this, just a Cartesian product. For example, the positive orthant is not primitive if the dimension is greater than 1, because it's just a product of positive orthants of dimension 1. The other standard cones that I mentioned before are primitive. Furthermore, if your cone K can be written as a Cartesian product, then its dual cone is just the Cartesian product of the primitive dual cones. All right, think inside the cone. So, in modern society, cones are also ubiquitous. It wasn't just, in Hypatia's time. It's a very relevant slide. So, we're going to define a primal conic form here. We're going to call it P. We're minimizing some linear function of the variables x, subject to an equality constraint, b minus ax equals 0. A is just a linear map. And this conic constraint, h minus gx, where g is a linear map, is in the cone. The conic dual can be written as such, and it has a similar looking form. We have an equality constraint and another conic constraint in the dual cone. Now we can actually write any convex optimization problem that's finite dimensional in the primal form there, or even in the dual form. And these tools called disciplined convex programming or DCP modeling tools actually automatically turn convex problems into conic form. So, conic certificates. If the pair, or the primal dual pair is what we call well posed, and I won't go into that, but almost always your problem will be well posed, then there exists a simple certificate that provides an easily verifiable proof of either, optimality of what we call a complementary solution, that's a primal dual solution, and that requires satisfying the feasibility conditions of the primal and the dual, and this strong duality condition that the objective values are equal, or a proof of infeasibility of the primal, which is what we call a dual improving ray, or infeasibility of the dual, which is a primal improving ray. And we have an algorithm that's cut off at the bottom, unfortunately. But, oh, frack. This is all the formatting's messed up. No. Now I'm spoiling all the great memes. Okay, so, yeah, it's cut off. But we have a solver called Pahirito, which does mixed integer conic optimization. and Pajarito is written hard-coded for only exponential, SDP, and second-order cones. But in the future, we will make a generic mixed-integer conic outer approximation solver. And so there's this algorithm that just takes the dual points from K star and solves mixed-integer conic problems. So watch out for that in Julia. Okay. Format completely messed up. So, how do we get these conic certificates? Hypatia. So, Hypatia is a highly configurable, open source conic interior point solver written in Julia, and it finds approximate conic certificates given some numerical tolerances specified by the user for that primal dual pair. It's accessible either through a native interface or through JuMP via MathOpt interface. So with the native interface, the data for the primal, we have C, B, and H are just vectors in Julia. A and G are linear maps, and K is specified as a vector of Hypatia primitive cone objects, which are just Julia structs. Our MathOpt interface wrapper takes an MOI problem and transforms it into that form and gives that data to Hypatia, and at the end it sort of reinterprets the certificates back into duals that MOI can return. And there's a point cut off that I can't remember what it said. Damn. All right. Generic cone interface. This is one of the main sort of highlights of Hypatia. So I don't know if we coined this or not, but bring your own barrier. So it allows the user to specify any primitive proper cone, K sub K, as a Julia struct. And the user only has to implement very few oracles. They need just one interior array that helps us get an initial starting point, a feasibility check for a point, and the gradient and Hessian of a barrier, which satisfies some properties. We don't need this information for both the primal and the dual primitive cones. We only need it for one or the other. And this is actually an algorithmic advance over the state of the art. Yeah, so you can construct your K as a Cartesian product of any combination of primitive cones or their primitive dual cones. So it's very general because there are some cones for which we have efficiently computable logarithmically homogeneous self-concordant barriers for either the primal or the dual, but not both. And the weighted sum of squares cone is actually an example of that. We have a barrier for the dual cone, but not for the primal cone. Okay, so Hypatia. Look, all of these different cones. These are standard cones that you might recognize. The first one is the second order cone. The second is the rotated second order cone. Then we have, that's the exponential cone in 3 dimensions and a particular power cone. But there are so many more cones that we could use rather than just the ones that other conic solvers recognize. So these cones you may not have heard of because they don't even have a name. So the epigraph of the infinity norm, and its dual cone, which is the epigraph of the L1 norm, the epigraph of the spectral norm, or its dual, or the epigraph of the nuclear norm. Power cones in higher dimensions, epigraph of the perspective of a sum of exponentials, the hypergraph of the perspective of the log determinant function, and these weighted sum of squares type cones. And there's actually many more that we have either implemented or plan to implement as sort of predefined ones that users can use, but you're not limited to the ones that we've predefined. Okay, so briefly about barrier functions. It must satisfy this logarithmic homogeneity condition here, which is fairly natural for cones, actually. And, it should satisfy self-concordance, but we've tried barriers that are not self-concordant, and Hypatia still usually manages to, well, it always manages to run. It doesn't come up with errors, but it can be a bit slower. It can take more iterations if you don't have a self-concordant barrier. Yep, and it's convenient to obtain the gradients and Hessians of your barriers if you use automatic differentiation, but for efficiency, for our predefined ones, we've actually gone and found analytical formulae for all of those. Okay, so our model interface. So the data that you provide in the form of the BCH and AG linear maps can be given in any real type that Julia recognizes. And actually, throughout the algorithm, there will be no loss of precision anywhere. There's no conversions to other types. So these linear maps can actually be, dense or sparse or block, triangular, any sort of structured types, or they could be specified just in terms of their matrix vector products and adjoint vector products. So potentially it could be extremely efficient for structured problems. Now, if A and G are dense or sparse, then we actually are able to do QR-based pre-processing and remove inconsistent inequalities and remove redundant inequalities and detect if the problem has inconsistent inequalities. And through the model interface, you could also pass in an initial point, kind of as a warm start even, or otherwise Hypatia will find it itself. So yeah, unlike other conic solvers, with Hypatia you could just specify linear operators. That could save you a lot of memory and potentially even time. All right, so solver interface is next. So the method that we've currently implemented is based on what's called the homogeneous self-dual embedding, which is the sort of basis for most interior point methods, conic interior point methods. And our algorithm is an extension of several methods, in particular these two. CVXOpt is a symmetric cone solver, so that's just a couple of the standard cones for which the cones are self-dual. And this algorithm by Skaja and implemented in a MATLAB solver called Alfonso is a non-symmetric conic IPM, but it's not as general as ours because we're able to use sort of primal or dual primitive cone barriers. We're going to talk about all these in a future paper, so I'm not going to do them here. But you can also define other types of solvers, and one would be for conic QPs, where actually there's in the objective a convex quadratic term. And that is implemented for symmetric cones in CVXOpt, and we want to do a non-symmetric extension of that. So Hypatia is designed to be very modular, and there are abstraction layers between all these major subroutines. So you can plug in your own routine anywhere. For example, you could utilize the structure of your problem to do faster linear system solves. All right, plug it in. Yeah, the matrix, which I haven't seen in 20 years, but whatever. All right, so to give a little intuition about the high-level algorithm, Hypatia is going to start at some initial frac. There, that wasn't, I didn't swear. All right. Okay, so, wrong button.
If you leave it out of full screen mode, you'll get your margins in.
Oh, thank you, thank you. All right, good point. I think I can get rid of this little toolbar. No, whatever. I'll just leave it there. Okay. Good point. Oh, but no, it's still changed the size of the text weirdly, so it's still cut off. Yeah. Okay. All right. Yeah, all the text sizes have changed. So Hypatia is going to start at an initial point, and that point will actually be on what's called the central path. And essentially, the central path is a solution to this ODE, and we're changing this sort of penalization parameter mu from 1, and we're going to take it to 0, and sort of try to follow this this solution of the ODE down to the optimal solution, which happens at mu equals 0. So we take this step, and then we're at this point here. I just pressed the laser pointer button and it goes back.
Use the mouse, actually.
Yeah. All right. Use the mouse. Okay. So this is our second point here, and we're going to calculate an affine direction and a correction direction. The correction direction tries to keep us close to the central path, and the affine direction tries to take us towards sort of the optimal solution a bit. And the reason we want to stay near the central path is there's a bunch of reasons, but sort of good numerics, and yeah, various complicated reasons. This is basically what all the conic interior point solvers do. All right, so at each iteration of the main loop, we're going to calculate the residuals of this KKT system, which is basically the residuals on our optimality certificate at the current solution. And then we're going to check these convergence conditions and finish with a certificate of optimality or infeasibility if some of these tolerances are met. Otherwise, we're going to solve a linear system for the affine and correction directions. We're going to perform a line search. Then we're going to use this heuristic formula to find a combined direction. And we're going to do another line search to see how far we can travel in that combined direction. And then finally, we're just going to step that sort of maximal distance alpha. So all of these sorts of steps, the user can modify them quite easily because there are nice abstraction layers. All right, so this is sort of the interesting part when it comes to applications and computations. So, all right, natural versus extended formulations. So a lot of convex problems can be represented through extended formulations using only that small number of, less than half a dozen standard cones recognized by other conic solvers. Not all of them, but that's kind of the union of what they can recognize. So we'd call those extended formulations because to actually get it representable with those cones, you often need to add more variables, more constraints. You blow out the size of the problem. And as such, the extended formulations can be larger and harder to solve in terms of time, memory, even numerics, than more natural conic descriptions where we are able to use a much broader array of cones. And the most time-consuming procedure in Hypatia, and actually all of these conic solvers, is solving a large linear system. And so if we can, have fewer variables, have fewer equality constraints, have lower dimensional cones, then we could potentially, really get rid of this bottleneck. It's also a lot easier to model with the natural formulations, as we'll see in some examples, because you don't have to worry about, oh, this is equivalent to this, blah, blah, blah. All right, so what was the point of this slide? Extended formulations are just sometimes too much. They're so much that it's just not even functional anymore. So why? Okay. Here's an example. Matrix completion. So we have some matrix M with some known entries and U unknown entries. And we want to minimize the spectral norm subject to this constraint that the missing values that we find have a geometric mean greater than 1. And the values that are known are matched. And this is just adapted from CVXPy. I don't know exactly why you want to do these things, but I don't care. So we're going to use two interesting cones here. One is the spectral norm cone, and that is the epigraph of the matrix spectral norm. And another one is this hypergraph of the geomean function. So clearly, you can just kind of plug them in there. And you haven't added any variables or really increased the dimension of anything. Whereas if you were to use an extended formulation, you would need a very large PSD cone of side dimension n plus k for that particular formula there, where sigma is the objective sort of epigraph variable. And you would need 3-dimensional, U minus 1 3-dimensional geomean or power cones to be able to use, say, MOSEC. These are the sizes of the two, clearly extended quite a bit larger, and we're going to compare performance. So here's what we've got. In the blue, we've got Hypatia's performance on the extended formulation. In the gray, we have a competitor, in fact, the most advanced commercial solver out there for this stuff, their latest version. Their performance on the exact same extended formulation that we use with Hypatia. And then finally in the red, we have Hypatia working on the equivalent natural formulation. And we've just generated this random instances with these sorts of sizes, set a tolerance on the certificates of 10 to the negative 5, and we're counting the time to converge as we increase the parameter k, which was one of the size of one of the sides of the matrix. And what we see here is that Hypatia on the extended dies from a time limit, which is 1800 seconds first. Then the competitor dies from actually, I believe, a memory limit, not a time limit, a memory limit at k equals 200. And Hypatia is able to keep going on the natural formulation. And we could have kept going if we'd increased the time limit. So here's another interesting feature I'll show off. Multiple precision in Hypatia. So on a particular instance of size 5.7, which is small, we're going to try passing in the data to Hypatia in some different Julia float types. So, and see how far we can go, what residuals we can get on the certificates. So if you look over there, mouse. What I have is what the name of the float type is, and float 128 comes from a package called QuadMath. There are different options for float 128. We have the epsilon. If you call eps of the type, that's what it gives. And then in the residuals column, we have the worst residual on the conic certificate, on the conic certificates that we achieve at using that floating point type, and before Hypatia dies. And actually, we tend to converge reliably to tolerances of almost exactly the square root of epsilon, and there's a sort of a reason for that. But you can see it with the timings. So with float 64, we're taking 1.33. We're taking a lot of iterations because there's some numerical issues there. And with big float 2048, that's using 2048 bits for the significand. It's going to take 135 seconds. And it's going to get to residuals, worst case residuals of 10 to the negative 304, which is insane. Yeah. All right, another example. Here we get to polynomial stuff. Don't worry, the rest of the talk is polynomial stuff. So we want to solve this global minimization problem of a polynomial that's given. And here's a sort of formulation whose format has been messed up. So we maximize a variable gamma. We're going to say that these sigmas are sum of squares, and in this constraint over here, we've got f of x minus gamma equals the sum of these parts, and over here we ensure that we're only dealing with the unit box. So in a natural formulation, we're going to use an interpolant basis weighted sum of squares cone, and that's sort of defined in this paper by Papp and Yildiz a few years ago, and explored by Nestorov 20 years ago. And it's only going to use one of these cones. So actually, the formulation you see here doesn't really correspond too closely, but it just has one equality constraint and one of these cones, and that cone has dimension the number of coefficients on the polynomials. The extended formulation is going to use m+1 PSD cones. Now I mentioned interpolant basis. I don't really have time to go into that, but in general, using an interpolant basis can give you very good numerics for a sum of squares. So Hypatia, we have a module called Model Utilities, which actually does pretty much the most advanced things for finding these good interpolations, and it allows you to use them in your modeling afterwards. Okay. Sizes were cut off, unfortunately, but here's our comparisons. All right, so again, same colors. Hypatia on the extended formulation in blue. U is the number of coefficients, which depends on n and d, or m and d, the number of polyvars and the degree of the polynomials we're considering. So our competitor is very surprisingly the same or even slightly worse than us, and they die from a memory error at u equals 3000. We don't die from a memory error at 3000 on the extended formulation. We run out of time. So this is very surprising because we are very dumb. We don't do anything special for SDP. And these are SDP problems. We're not using Nesterov-Todd scaling. We're not using any of this advanced symmetric cone stuff. So I don't know. I think maybe it's the linear algebra we're doing. But if you look at the natural, we blow the extended formulation out of the water, and that's because the dimension of the problem is just so much lower. The dimension of the one WSOS cone is much lower than the sum of the dimensions of all these PSD cones. So that's very favorable. Okay. How much time have we got? 15? All right, cool. So some applications of polynomial optimization and some more computations. Here's some cool, crazy applications that I'd love to work on at some point. Yep. So, okay, first one, shape-constrained polynomial regression. All right, formatting. So we want to fit a smooth function to some sample of data using a given convex loss objective, which we could formulate with cones because it's convex, while satisfying certain constraints on the shape of the function. So typical shape constraints might be monotonicity with respect to some of the variables, or convexity or concavity, or requiring the function to pass through the origin. And here we have results with an L2 norm objective, noisy data, signal to noise ratio of 10, or 0.1 rather. And the function that we're generating these points from is e to the norm of x, and x in this case is two-dimensional. And on the left we have the optimal unconstrained polynomial fit. So here we're just getting the best, we're not imposing monotonicity or convexity, because that function is monotonic and it is convex in reality. And on the right, you can see, we're not overfitting. We are imposing these conditions. And it's sort of nice and regularized. And it's actually truly monotonic and convex. So why? There are applications around the place that demand incorporating certain knowledge or theoretical assumptions about your function. If these assumptions are valid, then the shape constraints can significantly boost out-of-sample performance according to RMSE. So I'm going to skip that example because I got a real-world one. Here's some manufacturing data from these papers. And we're going to seek to predict the value of shipments from 4 independent variables. And we use an L2 norm loss objective. And, on the graph on the left, before that, so there are economic arguments and evidence that this value of shipment should be jointly convex and monotonically increasing with respect to the 4 independent variables that we care about. And on the top right, there's just for one of those variables, a graph of what it looks like. All right, as you can see, in the blue we have imposing convexity. In the orange we have imposing monotonicity. In the green we have no constraints. And on the left we have in-sample root mean squared error. And on the right we have out of sample. So clearly on the left, the unconstrained is doing very well because it's able to overfit. And on the right, the unconstrained has horrid errors because it is overfitted. And in fact, it seems that in this case, the monotonicity is the one to use. But we didn't try monotonicity and convexity, although we could have easily done that. It was just too many bars. All right, so another example, maximum likelihood density estimation. So given some number of observations, we want to find a smooth probability density that maximizes the log likelihood of the collected observations, and supported on some particular semi-algebraic set. So we're going to formulate a problem over polynomial functions, smooth, that are non-negative and integrate to 1 on this set. And we can optionally add shape constraints, just like we did for the regression problem. So we have 2 data sets. One is just the iris data set of the flowers. 50 data points and 4 dimensions, and we're going to use a degree 6 polynomial. And this lung cancer set, which has 82 data points, 7 dimensions, and we're going to use a degree 4 polynomial. Whew. Okay, at the top we have iris, in particular 2 different things, setosa, sepal length, and petal length, and whatever. Down the bottom we have lung cancer. As I said, that's a 4 degree polynomial in 7 variables, and we're just plotting a couple of those there. This is what that density that we estimated looks like, and those orange points are sample points, data points. So yeah, whatever. Here we have a computational comparison. So in the blue, so basically this problem is formulated with exponential cones for these log likelihood terms in the objective, and either a WSOS, weighted sum of squares cone, or PSD cones. So the extended formulation uses the PSD cones, the natural formulation uses the WSOS cone. The competitor is only able to use the PSD cones formulations. As we can see, for really small sizes below solve time 1 second, the competitor is winning, but above problems that take 1 second to solve, we're winning, and right at the end there we jump up to much better, and we should have kept going, but we just haven't had time. Yeah, so reasonably favorable. All right, another example. How much time I got? 10 minutes. All right, this is very brief. So here we have this Lotka-Volterra system, which is where you have predator, it's a predator-prey model. And we want to solve this infinite time discounted optimal control problem for harvesting rates, given some costs and whatnot. So do we cull the rabbits? Do we whatever? We have some objective of how many wolves we want. Or if we're fishing, we want to keep the fish population stable, and we get some profit from certain fishes. And this is from a particular paper by Korda, Henrion, and Jones. And if you calculate these for some particular data, here we have 4 species. On the left, you end up with these optimal harvesting rates. They're not polynomials. This is a simulation given the polynomial controls. And on the right, we have, okay, given those controls, what actually ends up being the populations over time, given some initial conditions. So we found the controls using optimization, and then we used ODE solver and Julia to actually run the simulation, kind of. All right. So now a crazy generalization of all this polynomial stuff. It's complex polynomial optimization. Oh, horrible. Okay. So a degree D polynomial in n complex variables. So our polyvars are now complex. We're going to look at this H, okay? So when I say degree D, that's actually in inverted commas because it's a different notion of degree. So we have these coefficients, complex coefficients H sub alpha beta. Beta and alpha are vectors in the non-negative integers, and z to the beta is a complex variable monomial. It's a complex monomial. And so what we see is we're summing overall alpha and beta vectors for which the components sum to less than or equal to d. So all monomials sort of vectors with total degree less than or equal to d. H, the coefficient, which is complex, times the conjugate of z to the alpha, which is just the conjugate goes through to all the little guys, times z to the beta. All right. Polynomial that looks like this is real valued if and only if the coefficients h are defined by a Hermitian matrix. And that's because you kind of get this cancelling out of all the imaginary parts. Now, a polynomial like this is Hermitian sum of squares if and only if these coefficients are defined by a Hermitian PSD matrix. this is totally messed up now, but never use Google Slides. Yeah, now we have a complex generalization of the polynomial minimization problem. So we're going to minimize over some complex polyvars in n dimensions a real valued polynomial function f subject to certain real valued polynomial functions gi being greater than or equal to 0. There's no convexity constraints or anything on those. It's just they have to be real valued. And we're going to transform this over on the right into this particular formulation. And the x variables here are the optimization variables, and that w is a particular, it's a w-sauce cone that's defined by the data of the problem. All right, here's some tiny examples of, polynomial minimization problems with closed form solutions. So obviously, minimizing 1 plus the norm of z it has the minimum 1 because you get z at the origin. And there's some other interesting ones on interesting sets like, unit complex ball and whatnot. Application. Okay, optimal power flow. So Cedric Joss and Daniel Malzahn have had some recent papers where they explore complex polynomial optimization models, in particular just a simple global minimization over a semi-algebraic set type problem with complex polyvars for optimal power flow problems. And so this is a formulation here, and actually this formulation is simply, the same as this minimize f subject to g sub I greater than or equal to 0 with complex guys. And so they don't know about W-sauce, so they're using MOSEC or whatever with real PSD cones. So they're doing several transformations where they're actually identifying the real and imaginary parts with 2 real polyvars. That's one type of formulation. So you make the polynomial optimization problem real with twice the number of variables, and then you go and solve a relaxation of it. They show that no, if you first come up with the relaxation before identifying real and imaginary parts, and then go and turn this complex relaxation into a real relaxation, that you can get a much better problem to solve, SDP problem. And those things are not commutable. The sauce relaxation and the identifying the imaginary and real parts are not sort of commutable. So they go and do this alternative way, and they turn their complex relaxation into a real semi-definite program and go and solve that. And they prove some interesting things. First of all, that a convergent complex hierarchy exists, analogous to the real hierarchy, but it requires a sphere constraint rather than a ball constraint to sort of get that convergence to go through. However, that's not restrictive. And they for a fixed order D, they show that the Hermitian sauce relaxation is 2 to the D minus 1 times smaller than the real sauce case, where they've identified first. However, the Hermitian sauce bound is equal or poorer than the sauce bound. But, interestingly, for all of the OPF problems that they tested, the complex and the real bounds were actually equal. So they speculate that maybe there's something about OPF that means that Hermitian much smaller Hermitian sauce relaxations are equivalent. Well, they get the same objective at the same order. But there's no proof there yet. Okay. In Hypatia, you have several different ways that you could formulate this type of problem. You could do the identifying real and imaginary, get the real sauce formulation, which will say that way of doing things is R. Or you can first do the sauce relaxation and then later maybe go and turn it into real, and that's C. So they're not equivalent. But for each of those, you can either do a SDP formulation or a W-sauce formulation. And we've generalized these the W source cone, the weighted sum of squares cone, to the complex case, and we've generalized the barriers and the interpolation and everything like that, which was non-trivial, but it looks very nice. The math is just very simple. And so we can do, Hypatia actually has a Hermitian PSD cone defined in it. So if you were to use MOSEC, you would have to do this formulation where you sort of double the side dimension of the matrix, and it's quite a bit larger. With Hypatia, you can just pass in, the real diagonal and the complex and imaginary parts of the subdiagonal, and we will use a complex arithmetic in Julia to actually do the barrier stuff. And there's some computational questions here, and more importantly, if we want to use this stuff through the interfaces, multivariate polynomials, polyjump, sum of squares, moment opt, that we've been talking about for the rest of the time here, then we're going to need to generalize the polyvars for complex case. And that's sort of non-trivial. If you want to help, let us know. And I don't have time for that, so we're done.